Hello everyone, my name is Giudice and I am a PhD student at Politecnico di Torino. My research focuses on improving the scalability and interoperability of AI-based decision support systems for enhancing energy management in buildings. Decision support systems are a family of tools that automatically analyze building-related data, providing stakeholders with insights about the performance of their buildings and identifying energy-saving opportunities. These opportunities are even more enhanced by the recent integration of artificial intelligence within building information systems. These tools mainly work at three different scales. At the system level, with the objective to identify and diagnose faults in building energy system and components. At the building level, to assess building's performance and identify the occurrence of anomalies. And eventually, at the multiple building level, with the aim of comparing energy performance in cluster of buildings with a focus on aspects related to energy demand flexibility and grid interactions. Despite their potential, the widespread adoption of these tools in commercial and industrial buildings faces some barriers. Some of the most significant challenges pertain to generalization, the transferability of applications, the need for defining self-tunable analytics processes, and in some cases the need for overcoming the lack of training data are the main challenges for an effective deployment. To address these challenges, such AI-based solution should exploit an a priori domain and physics knowledge to ensure their optimal performance in field. Another issue is the lack of scalability and portability of these analytics tools, mainly caused by the absence of a unified way to describe or represent building-related data. To overcome these, integrating ontologies including building metadata and semantic data description is essential for the broader adoption of these tools. In this context, in my first year, I focused on applications at the multiple building level aiming to generalize time series-based external energy benchmarking processes. In particular, a framework for evaluating and comparing performance of more than 600 non-residential buildings was developed. One significant contribution is the introduction of a novel step called peer identification, which dynamically identifies within an existing large stock of buildings a baseline group against which benchmark the 1 year electrical energy consumption of an auto-sample building. The proposed methodology takes into account a distinctive feature of building electrical energy consumption time series, including thermal sensitivity, shape, and magnitude, and introduces KPIs related to the electrical load volatility, the rate of anomalous pattern, and the building operational schedule. This innovative approach significantly enhances the accuracy of the benchmarking process when it is compared with a conventional approach only based on the comparison with the buildings belonging to the same end-use category. As a matter of fact, an improved accuracy of about 14% for the calculated KPIs is observed for a testing set of buildings. In the future, my research activities will focus on the generalization of fault detection and diagnosis processes through the injection of physics and domain knowledge, the introduction of a scalable ontology-based framework to improve energy management in a real-case scenario of aggregates of residential buildings, and finally, the investigation of semantic interoperability in the context of demand energy flexibility of buildings. Thank you.